Welcome back to the Deep Dive, listeners. Today we're taking a look at something that's got me pretty intrigued.
Oh, I'm all ears.
Well, we've been talking a lot about quantum systems lately, all the weirdness with superposition and entanglement and, the whole nine yards.
Right. The quantum world, always keeping us on our toes.
Exactly. And one thing that just keeps popping up is this problem of information loss, like how these systems are super fragile and the information just seems to, I don't know, fade away.
Yeah, it's a bit of a head scratcher, isn't it? I mean, even with all the advancements we've made trying to control these quantum systems, it's like there's this inherent leakiness. We're always fighting against it.
Right. And it's not just a theoretical curiosity. It's like a major roadblock for building, say, reliable quantum computers.
Absolutely. If we want to build these futuristic machines that everyone's dreaming of, we need to get a handle on this information loss problem.
So that's what this deep dive is all about.
Love it. Let's dive in.
So I've been reading up on this, and it seems like there are a few ways we already measure this loss.
Yeah, so like quantum state fidelity, right? That tells us how much two quantum states overlap. If they're very similar, the fidelity is high. But if they've drifted apart because of information loss, well, the fidelity drops.
Okay, so fidelity gives us a snapshot of how the state has changed. What else?
Well, there's coherence, which is like, the heart of quantum mechanics. It's that ability of a system to be in multiple states at once.
Superposition. Right?
Yeah, exactly. And when we lose information, we often lose coherence. So measuring how much coherence is left gives us another clue about how much information has slipped away.
Got it. And then there's von Neumann entropy.
Right, entropy. That's a measure of how mixed up a quantum state is. The more mixed up it is, the more information we've lost. So tracking the change in entropy gives us yet another way to look at this problem.
So we've got fidelity, coherence, and entropy. 3 ways to quantify information loss.
Pretty much.
But the real rabbit hole I wanted to jump into today is something called the SIN information integral.
Now you're talking. This is where things get really interesting.
So I gotta admit, the sources I've been looking at, they don't really give us a neat, clean definition of what this SII thing actually is.
Yeah, that's part of the fun though, right? Trying to piece together the puzzle.
Exactly. But there are some tantalizing hints.
Like the sin part itself. It kind of screams, sine waves, trigonometry, all that fun stuff.
Right. Specifically, I kept thinking of the sinc function, sin of x over x or sin of pi x over pi x, depending on who you ask.
The sinc function. Now, there's a workhorse in signal processing. It's all about decomposing signals into their frequencies, doing Fourier analysis.
And that makes me wonder, is this SII somehow analyzing information loss from a frequency perspective? Like, are some frequencies of information more prone to disappearing than others?
Now, that's a fascinating thought. And it's not entirely out there. If you look at some of the mathematical breadcrumbs in the sources, you see hints that this SII might involve integrals, calculus stuff, where you're integrating something related to the quantum state, like its density matrix, multiplied by a sinc function.
Okay, hold on. Density matrix, just a quick reminder for our listeners.
Sure. Think of it as a mathematical object that captures all the information about our quantum system, all the possibilities and probabilities baked in.
Right. So are we basically taking this density matrix, evolving it in time, and then filtering it through a sinc function to see how the information content changes over different frequencies?
That's one way to picture it, yeah.
Yeah.
It's almost like we're looking at the information content of the system through a very specific lens, one that focuses on frequencies.
So instead of just looking at the overall state, we're zooming in on different frequency bands.
Exactly. And that could give us a whole new layer of understanding, right? Like maybe certain frequencies are more susceptible to noise or decoherence, and this SII could help us pinpoint that.
Okay, I'm starting to see where this is going, but the sources also mention just basic sine integrals, not just the sinc function. So could there be other forms of this SII?
Oh, absolutely. For example, maybe we're integrating the sine of some distance measure between the initial quantum state and the current state.
Distance measure, as in how far the state has evolved?
Yeah, exactly. Like, how much the information has been scrambled. And integrating the sine of that distance could capture any kind of oscillatory behavior in the information loss. Like maybe it's not a smooth decline, but it goes up and down as the system evolves.
Oh, so we're not just seeing how much information is lost, but how it's lost, like the pattern of the loss.
Right. Or another possibility, maybe we're integrating some kind of observable, a property of the system that carries information, but it's filtered through a sine wave at a particular frequency.
So again, we're zooming in on specific frequencies.
Exactly. And that could tell us how that specific type of information at that frequency is decaying over time.
Okay, so lots of potential forms for this SII. But the one thing that seems constant is the focus on how the quantum state is changing over time.
That's the key. It's not just about the final state, it's about the whole journey. It's like a quantum road trip.
I love that.
Where are we going? Who knows?
Right. But we're tracking every twist and turn, every bump in the road to see how the information changes along the way.
Couldn't have said it better myself.
So let's say this SII does pan out. It actually gives us useful information. How does it stack up against the tools we already have? Like, how would it be different from fidelity, for example?
Well, think of it this way. Fidelity is like a single photograph, a snapshot in time, showing you how blurry an image has become. The SII, on the other hand, is more like a video. It shows you the whole process of how the blur developed. Maybe it happened gradually, maybe there were some sudden shifts.
Ah, so we get a more dynamic view of the information loss, not just a single data point.
Precisely. And it's not just about being more dynamic, it's about seeing things that fidelity might miss entirely. Like, imagine you have this video of the image blurring and you notice that there are these weird oscillations in the blurriness. It gets blurry, then sharpens a bit, then blurs again. Fidelity wouldn't catch that, but the SII might, because it's looking at the whole evolution over time.
Okay, so that's how it differs from fidelity. What about coherence?
Well, coherence measures, they give you the overall amount of superposition, right? Like how much quantumness is left in the system. But the SII, with its potential focus on frequencies, might tell you which superpositions are the most fragile, which ones are decaying the fastest.
So it's not just about how much quantumness we're losing, but what kind of quantumness we're losing.
Exactly. It's like, if you're listening to a symphony orchestra and some of the instruments start to go out of tune, a coherence measure would tell you that the overall harmony is decreasing. But the SII might be able to pinpoint which instruments are causing the problem.
And what about von Neumann entropy?
Entropy is a measure of overall uncertainty, right? Like how mixed up the quantum state has become. But the SII, especially if it's capturing those oscillations we were talking about, it might be able to reveal specific types of correlations that are being lost. Correlations that wouldn't necessarily show up as a simple increase in entropy.
So it's like looking under the hood, seeing the detailed mechanisms of information loss, not just the overall effect.
Yeah, exactly. It's getting to the nitty-gritty.
Okay, so big picture. If this SII lives up to its potential, what are some of the things we could actually do with it?
Well, for one, it could be a huge boon for benchmarking quantum computers. Right now, we're still figuring out how to measure how well these machines actually perform. And being able to quantify information loss in this detailed way, that would be a game changer.
So we could compare different quantum computers, see which ones hold on to information better, or test how well a particular quantum computer is performing over time.
Exactly. And not just that, we could potentially use the SII to identify the dominant noise sources in a system. Like maybe we see a certain pattern of information loss that tells us, this looks like it's mainly due to thermal noise. Or maybe it's magnetic field fluctuations causing the trouble.
So we could diagnose the problem, not just observe the symptoms.
Right. And that knowledge could lead to better ways to mitigate those noise sources.
Okay, what else?
Well, another exciting possibility is using the SII for real-time error monitoring. Like imagine you're running a quantum computation and the SII suddenly spikes. That could be an early warning sign that something is going wrong, and we could potentially take corrective action before the whole computation crashes.
So like a quantum smoke detector.
I like that analogy. Yeah, like a smoke detector that tells us, hey, something's heating up here, better take a closer look.
Okay, this is all sounding pretty awesome. But I know there are always limitations, right? Like, this SII is not a magic bullet, is it?
Oh, of course not. No free lunches in physics, right? So one limitation is that it's likely bounded by the initial information content of the system. Like, you can't magically recover information that was never there to begin with.
Makes sense. What else?
Well, another thing to keep in mind is that the SII might be more sensitive to some types of noise than others. So we might need to use it in conjunction with other metrics to get a complete picture of what's going on.
So not a replacement, but a powerful addition to our toolkit.
Exactly. And then there's the computational cost.
Ah, yes, the age-old problem.
Calculating the SII, especially for large quantum systems, it could be quite computationally demanding.
And that means more time, more resources, more headaches for the poor researchers.
Right, right. So we might need to develop clever approximation methods. Actually, there's a cool parallel here with techniques used in AI and even speech processing.
Oh, yeah.
Like in AI, there's this thing called SHAPIQ, which is used to explain the decisions made by complex machine learning models. And it turns out that calculating SHP values exactly can be super expensive. So people have come up with these really clever approximation methods. And similarly, in speech processing, there are ways to approximate the SII for analyzing audio signals. So we can probably borrow some ideas from those fields.
So a lot to learn from other areas, as always.
Cross-pollination, it's the spice of scientific life.
I like that. Okay, so we've got limitations, we've got computational challenges. What about future research? Where do we go from here with this SII?
Well, one really exciting avenue is integrating the SII with feedback control. Like imagine we're monitoring the SII in real time, and if it starts to creep up, we automatically adjust the control parameters of the quantum system to try and bring it back down.
So we're not just watching the information leak away, we're actively fighting back.
Exactly. It's like, if you're sailing a boat and you start taking on water, you don't just sit there and watch it sink, you start bailing water out.
Love the analogy. What else?
Well, I think machine learning has a huge role to play here. We could potentially use machine learning to predict how the SII will evolve over time, or to optimize the control parameters of a quantum system to minimize information loss.
So using AI to fight information loss in quantum systems, that's pretty meta.
It's the future, my friend.
I'm all for it. Okay, any other research directions that come to mind?
Well, I think it would be really interesting to do comparative studies across different quantum hardware platforms. Like maybe some types of qubits are inherently better at retaining information than others, and the SII could help us quantify that.
So it could guide the development of better quantum hardware.
Exactly. And finally, I think it would be really cool to apply the SII to the study of quantum interference. Like how does noise affect the delicate dance of quantum waves? Can the SII give us a new perspective on that?
Wow, so many possibilities.
That's the beauty of it.
Yeah.
We're just scratching the surface here.
Okay, so to wrap up our deep dive today, while the SIN information integral isn't fully defined in the sources we looked at, it offers a really fascinating potential new way to think about and quantify this fundamental challenge of information loss in quantum computing.
It's a whole new lens to view the quantum world through, and I'm excited to see where it takes us.
I am too, and I'm curious, for our listeners out there thinking about what we've discussed today, about this idea of a SIN information integral and how it might be connected to frequencies and the evolution of quantum states, what specific aspects of quantum information loss do you think this SII could uniquely reveal? It's a question worth pondering.
Definitely food for thought.
Until next time, keep exploring the quantum mysteries.
And keep diving deep.